welcome to this problem walkthrough. Today, we'll explore problem number 107, Binary Tree Level Order Traversal 2. In this problem, we'll focus on traversing a binary tree and exploring its levels in reverse order. Let's dive in and break this down step by step. In this problem, we're working with a binary tree, and our goal is to return the bottom-up level order traversal of its nodes values. This means we'll traverse the tree level by level, starting from the leaf nodes at the bottom, and work our way up to the root. The input is the root node of the binary tree. Each node contains an integer value, as well as references to its left and right child nodes. For the output, we need to produce a list of lists, where each sublist represents the values of nodes at a specific level. These levels should be ordered from the bottommost level of the tree to the topmost, or root level. Let's look at some examples to clarify this further. In our first example, the binary tree has 3 levels. At the bottommost level, we have the nodes with values 15 and 7. At the second level, we have nodes with values 9 and 20. Finally, at the root level, we have the node with value 3. For the bottom-up level order traversal, we start with the bottommost level and move upwards. So, the output is a list of lists, 15, 7, 9, 20, 3. In the second example, we have a tree with just one node, the root, which has a value of 1. Since there's only one level, the output is simply 1. Now let's move on to a slightly more complex case. In the third example, the binary tree has 3 levels. At the bottommost level, we find the nodes 4 and 5. Moving up to the second level, we have nodes 2 and 3. Finally, at the root level, there's a node with value 1. When we arrange these levels in bottom-up order, the output becomes 4, 5, 2, 3, 1. This demonstrates the core idea of traversing the tree level by level from the bottom to the top. Now let's consider the constraints and edge cases to ensure our solution is robust. The problem comes with some important constraints and edge cases to consider. First, the number of nodes in the tree can range from 0 to 2000, so we need to handle small and large trees efficiently. The values of the nodes are integers, ranging from -10,000 to 10,000. For edge cases, if the tree is empty, meaning the root is null, the output should be an empty list. If the tree contains only a single node, the output will be a list with just one sublist containing that node's value. The function should also handle unbalanced trees, or all nodes might be skewed to one side, and ensure that nodes at the same depth are grouped correctly even if some branches terminate earlier than others. These considerations will help us craft a solution that works for all valid inputs. To begin, let's consider the first approach, a brute force method using recursive depth calculation. The intuition here is to traverse the binary tree recursively and calculate the depth of each node as you go. For each depth, you store the nodes in separate lists or a dictionary. Once this is done, you reverse the collected lists to achieve the desired bottom-up order. The steps involve defining a helper function to handle the recursive traversal, using a data structure to organize nodes by their levels, and finally reversing the order of these levels. While the time complexity is O(n), since all nodes are visited, there's an additional step to reverse the list at the end. Space complexity is O(h) for the recursion stack, where h is the height of the tree, and O(n) for the storage of nodes. The main advantage of this approach is its simplicity, but the need to reverse the list introduces extra work, which can feel inefficient. Next, we move to a more efficient solution, an iterative level order traversal using a queue. This approach uses a standard breadth-first search or BFS to traverse the tree level by level. As you process each level, you collect the node values and add their children to the queue for future processing. The key difference here is how you handle the result. Instead of building the result list in a forward order and reversing it later, you directly insert each level's values at the beginning of the result list. This eliminates the need for a separate reversal step. The time complexity remains O(n), as each node is processed exactly once, and the space complexity is O(n) for the queue, which holds at most one level of the tree at a time. The trade-off here is that inserting at the beginning of a regular list can become costly for large levels, so careful handling is required to maintain efficiency. Finally, the chosen approach is an optimized BFS that leverages a DEEC for efficient processing. The key observations leading to this choice are that the problem naturally aligns with BFS for level-by-level traversal and that using a DEEC allows for efficient front insertions, which is crucial for building the result in reverse order without extra overhead. Recursive methods, while simpler in concept, introduce unnecessary overhead due to recursion depth and list reversal. This optimized approach involves processing the tree level by level using a queue, storing the levels in a DEEC as they are processed, and finally converting the DEEC into a list before returning the result. It maintains a time complexity of O(n) and a space complexity of O(n). The trade-offs are minimal. While a DEEC may be slightly more complex to use compared to a regular list, it significantly improves performance for this problem. In conclusion, this strategy offers the best balance of simplicity, efficiency, and scalability, making it the ideal solution for traversing the tree and building the bottom-up level order directly. To solve the problem of bottom-up level order traversal in a binary tree, we aim to return node values level by level, starting from the bottommost level. The brute force approach involves recursively calculating the depth of each node, grouping nodes by their respective depths, and then reversing these groups to achieve the bottom-up order. The process begins by defining a helper function, traverse, which handles the recursive traversal of the binary tree. This function needs to manage the base case where a node is none, ensuring that leaf nodes are properly handled. Additionally, a data structure, such as a list of lists, is used to store node values grouped by their depths. This sets the foundation for organizing the nodes efficiently during traversal. The key to grouping nodes by depth is dynamically expanding the data structure as we traverse the tree. If the current depth exceeds the size of the list of lists, we append an empty list to the structure to accommodate the new depth. Once the structure is ready, the value of the current node is appended to the list corresponding to its depth. The recursive traversal then continues for the left and right children of the current node, incrementing the depth parameter for each child. After visiting all nodes, we reverse the list of lists to achieve the desired bottom-up order. This reversal ensures that the deepest levels appear first in the final result, while the root level appears last. The approach relies on recursive depth tracking to ensure that nodes are grouped correctly without requiring a separate traversal to calculate depths. This optimization reduces computational overhead. The reversal step, performed after the traversal, is efficient and straightforward, as it simply inverts the order of the groups. The algorithm handles edge cases gracefully, including scenarios with an empty tree, where we return an empty list, and a single node tree, where the result is a list containing a single list with the node's value. In cases of unbalanced trees, the algorithm adapts naturally, as the recursive traversal effectively manages subtrees of unequal depths without additional complexity. For this solution, we rely on two main data structures. First, a list of lists is used to group node values by depth, with each depth corresponding to a specific sublist. For example, in a tree with nodes 3, 9, 20, null, null, 15, 7, the list before reversal would look like 3, 9, 20, 15, 7. Second, the recursive call stack is implicitly used to traverse the tree in a depth-first manner. The depth of this stack corresponds to the maximum depth of the tree. Together, these structures enable an efficient and clean implementation of the bottom-up traversal. Analyzing the complexity, the time complexity of the algorithm is O(n), where n is the total number of nodes in the tree. Each node is visited exactly once during traversal. Operations such as appending node values to lists and reversing the data structure are O(1) and O(d), respectively, where d is the maximum depth of the tree. Space complexity is also O(n), driven by two factors: the list of lists used to store node values and the recursion stack used during traversal. In the worst-case scenario of a completely unbalanced tree, the recursion stack depth can reach O(n), but in a balanced tree, it would be proportional to the logarithm of n. The Python implementation of the algorithm begins by defining the level order bottom function, which initializes an empty list called result. A helper function, traverse, performs the recursive traversal. Within this function, if the current node is none, we return immediately. Otherwise, we ensure the result list has enough space for the current depth by appending an empty list if needed. The current node's value is then added to the appropriate list. Recursive calls are made for the left and right children, incrementing the depth each time. Finally, the traversal starts from the root node at depth 0, and the result is reversed to produce the bottom-up order. This implementation is concise, efficient, and handles all edge cases seamlessly. Here, we start by importing the Deek class from the Collections module, which will help us efficiently manage the queue for our level order traversal. Next, we define a tree node class to represent the structure of each node in the binary tree. Each node has a value, along with optional left and right child nodes. After that, we define a solution class with a method called levelOrderBottom. This method takes the root of the binary tree as input. The first thing we do inside the method is check if the root is none. If it is, we return an empty list since there's no tree to traverse. If the root exists, we initialize a queue using Deek and start it off with the root node. We also create an empty result list, which will eventually hold the levels of the tree. Then, we enter a while loop that continues as long as there are nodes in the queue. Inside the loop, we initialize an empty list called level to store the values of the current level. We then use a for loop to iterate over all the nodes currently in the queue. For each node, we remove it from the queue using popLeft, add its value to the level list, and check if it has left or right children. If it does, we add those children to the queue for processing in subsequent iterations. Once we've processed all the nodes at the current level, we append the level list to the result list. This ensures that each level is added in order from top to bottom. After the while loop completes, meaning we've traversed all the levels of the tree, we return the result list reversed using slicing. This reversal gives us the bottom-up order of the levels as required by the problem. By appending each level to the result during the traversal and reversing it at the end, we efficiently achieve the desired output without unnecessary overhead. Here, we start by defining the structure of a binary tree node using the TreeNode class. Each node contains an integer value, a left child, and a right child. We provide three constructors, one with no arguments, one that initializes the value, and one that initializes the value along with the left and right children. Next, we define the solution class, where the main method levelOrderBottom is implemented. This method is designed to perform a level order traversal of a binary tree, but instead of returning the levels from top to bottom, the levels will be returned in reverse order, from bottom to top. The first step in the method is to handle the edge case where the root is null. If the tree is empty, we simply return an empty list. Now, we initialize a queue to facilitate the level order traversal and a list to store the final result. The root node is added to the queue as the starting point. We then enter a while loop that continues as long as the queue is not empty. Inside the loop, we determine the number of nodes at the current level using the queue size and create a new list to store the values of these nodes. Using a for loop, we process each node at the current level by polling it from the queue, adding its value to the level list, and checking if it has left or right children. If it does, these children are added to the queue for the next level. After processing all nodes at the current level, the level list is added to the result. Once all levels are processed, we reverse the result list to achieve the bottom-up order and return it as the final output. Here, we have a basic binary tree with the root node 3, which has two children, 9 and 20. Node 20 further has two children, 15 and 7. To traverse this tree in a bottom-up level order, we start by initializing the queue with the root node 3 and an empty result list. As long as the queue is not empty, we process each level. Initially, the queue contains only the root, so the level size is 1. We dequeue the root node 3, add it to the current level list, and enqueue its children 9 and 20. This completes the first level, and we append the list 3 to the result. Now, the queue contains nodes 9 and 20, and we proceed to the next level of the tree. At the next level, the queue has two nodes, so the level size is 2. We start by dequeuing node 9, adding it to the current level list, and since it has no children, we don't enqueue anything. Next, we dequeue node 20, add it to the level list, and enqueue its children, 15 and 7. This forms the level 9, 20, which we append to the result. Now, the queue contains nodes 15 and 7, and we move to the final level. At this level, there are again two nodes, so we initialize a new level list. We dequeue node 15, add it to the level list, and since it has no children, we don't enqueue anything. Similarly, we dequeue node 7, add it to the level list, and leave the queue empty. This gives us the level 15, 7, which we append to the result. Since the queue is now empty, the traversal is complete, and reversing the result gives the final output, 15, 7, 9, 23. In the case of a single-node tree, the process is straightforward. The tree consists of just the root node 1. We initialize the queue with the root and the result as an empty list. The queue contains only one node, so the level size is 1. We dequeue the root node, 1, add it to the current level list, and since it has no children, we don't enqueue anything. This completes the level, 1, which we append to the result. With the queue now empty, the traversal is finished, and reversing the result gives the output, 1. To summarize, this algorithm uses a breadth-first search approach to traverse the binary tree level by level. A queue is employed to manage the nodes at the current level, while the result list accumulates values for each level from top to bottom. By reversing the result at the end, we achieve the desired bottom-up level order traversal. The algorithm efficiently handles edge cases such as single-node trees, where there's only one level to process, and empty trees, where the result is immediately an empty list. This approach ensures correctness and clarity for all input scenarios. Here, we analyze the time complexity of the solution. The primary operation in our algorithm is the breadth-first search, or BFS, traversal. Using a queue, we visit each node exactly once and enqueue its children, if any. Visiting each node once results in a time complexity of O(n), where n represents the total number of nodes in the binary tree. Additionally, for each level in the tree, we iterate over all the nodes present in the queue. Since the number of iterations across all levels collectively equals the total number of nodes, this step also contributes O(n) to the time complexity. Finally, we reverse the result list to achieve the bottom-up order. Reversing a list with k elements takes k time, and because the list contains n elements, this step also adds O(n). When we combine all these operations, the overall time complexity remains O(n). Now, let's consider the space complexity. The first component to account for is the space occupied by the queue during BFS traversal. In the worst-case scenario, such as in a complete binary tree, the last level contains the maximum number of nodes, which can be approximately n/2. Thus, the queue may require O(n) space in this case. Next, the result list stores all node values grouped by their levels. Since each node is stored exactly once, the space required for storing the result is also O(n). Furthermore, temporary variables like the level list used during traversal require space proportional to the number of nodes in the current level. However, this space is already factored into the queue storage. Adding these together, the total space complexity of the solution is O(n). We can further analyze this solution by considering best, average, and worst-case scenarios. In the best case, the tree is empty, with the root being none. Here, the algorithm terminates immediately, requiring only O(1) time and space. For an average case, where the tree is balanced with a height of log n, the algorithm processes all nodes level by level, resulting in a time and space complexity of O(n). In the worst case, where the tree is skewed into a single branch, the algorithm still processes all nodes sequentially, maintaining O(n) time and space. Compared to a naive approach that would traverse the tree repeatedly for each level, resulting in O(n)² time complexity, this optimized solution reduces the time complexity to O(n) by leveraging BFS to traverse the tree in one pass. Finally, let's solidify our understanding with a mathematical proof of the big O analysis. Each node in the tree is visited once during the BFS traversal, and each visit involves O(1) work. With n nodes in the tree, the total work becomes n multiplied by O(1), which simplifies to O(n). For space, the queue temporarily holds nodes at the current level, and the result list stores all node values. Both are proportional to the total number of nodes, leading to O(n) space. Additionally, temporary variables and operations like list slicing do not exceed the O(n) space bound. Thus, we conclude that this solution is optimal for performing a bottom-up level order traversal of a binary tree, achieving an impressive O(n) time and space complexity. When solving this problem, there are several common mistakes to watch out for. One major issue is misunderstanding how to calculate depth recursively. If you use the same accumulator for all depths instead of separating nodes by their respective levels, you won't group the values correctly. To fix this, make sure you use a clear structure, like a dictionary where the keys represent depths, to organize nodes as you traverse the tree. Another frequent pitfall is performing traversal inefficiently. For instance, calculating the depth of the tree first and then processing nodes separately can significantly increase the time complexity. Instead, aim to combine these steps into a single traversal. Additionally, forgetting to handle the base case and recursion can lead to runtime errors. Always ensure your base case is well defined, such as returning 0 for depth if the node is null. Finally, if you're implementing a bottom-up traversal, be careful not to skip the final step of reversing your results. After you've collected nodes level by level, reversing the output is essential for the correct order. Another mistake to avoid is overcomplicating the solution. Adding unnecessary data structures or multiple passes, like explicitly sorting depths, often leads to inefficiency. Instead, keep your solution simple and avoid redundant operations. Now, in the context of interviews, there are a few key things to keep in mind. Depth-first traversal, or DFS, is a common strategy for tree problems, and interviewers may specifically test how well you can implement a clean, recursive solution. So, practicing recursion with clear base and recursive cases is crucial. Also, focus on optimizing your solution to achieve O(n) time complexity, where n is the number of nodes in the tree. Redundant traversals can hurt performance and should be avoided. Lastly, while coding, make sure to communicate your thought process clearly. Whether you're explaining your recursive approach or your choice of data structures, clarity is just as important as correctness in an interview setting. Flexibility is another important skill to demonstrate. Be ready to adapt your solution for variations. For example, you might be asked to return values only for specific depths, handle duplicate values in the tree, or even modify the traversal to meet specific conditions. Practicing related problems can help you prepare for these variations. For instance, LeetCode 102 focuses on a top-down level order traversal, which is the reverse of this bottom-up approach and is great for practicing level-wise traversal in general. LeetCode 107, the problem we're discussing, is directly related, as it emphasizes collecting nodes from the bottom up. LeetCode 104, which involves calculating the maximum depth of a binary tree, is another useful problem to practice, as it reinforces depth-related concepts. Finally, LeetCode 543, the diameter of a binary tree, is another excellent example. It challenges you to calculate depth while focusing on the distance between two nodes, further strengthening your understanding of tree traversal techniques. There are also alternative approaches you can use to solve this problem. One option is an iterative approach using breadth-first search, or BFS. By using a queue, you can perform a level order traversal and store nodes based on their depth. While this approach avoids the risk of recursion stack overflow for deep trees, it does require additional memory for the queue. Another method is post-order traversal, which processes child nodes before their parent. This naturally aligns with the bottom-up order required in this problem. However, you'll need to carefully manage how you collect results to ensure the order is maintained correctly. Finally, you can use a modified pre-order traversal with depth tracking. By passing the depth as an argument during traversal, you can collect nodes at each level as you go. While this method is simpler to implement, it may require additional data structures to organize nodes based on their depth. Each of these approaches has trade-offs, so it's important to understand their strengths and limitations when deciding which one to use. Great work! To recap, we used BFS to tackle problem number 107 and learned how to traverse a binary tree level by level in reverse order. Remember, practicing tree traversal and understanding BFS are essential for technical interviews. Thank you for watching, and be sure to like and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!